Hello, this is Dr. Liu. In this video, I will derive the formulas that we use in Newton's second law lab. So this is the formula here. So we have the acceleration, which is equal to mass. This is the suspended mass over the total mass, which is the sum of these two masses times little g. So how do we get to this conclusion? Well, we'll start from the beginning by analyzing forces. So let's start with this mass, big M. We'll draw a free body diagram for big M. So here's M. We'll start with gravity, Fg, capital M. And then this is the normal force from the air, basically a thin layer of air, because this is on an air track. And then there's also a forward force. We call this tension. This is tension on that string. So I'll put capital M here. And I can write equations. In x direction, we have net force in x equals capital M AX. And in the y direction, we have net force in y equals capital M AY. But we know we set up our axis to be along these directions, and there's no acceleration in y. So this is equal to 0. So let me put in these choices of the axes. This is pretty obvious, but in some other situations it may not be obvious. So that is our axes. Okay. So the x force, there's just one force, tension. Tension equals capital M acceleration x. And in the y direction, we have normal force in the positive y direction and gravity in the negative y direction. I'll replace it with mg. That is equal to 0. Okay, we don't really need to solve this because normal force doesn't help us with anything. If we had friction, then normal force would be related to the frictional force. So that's not the case here. We can certainly solve it. We'll just say Fn equals mg. That's it. And in here we have two unknowns. Tension is unknown. The acceleration is also unknown. So we'll have to analyze the other mass, this little m, lowercase m. So we'll draw the lowercase m here. And we'll start with gravity as well. So Fg lowercase m. And this m is being pulled upward by tension. And these are the two same magnitudes of tension, except that their directions are different because we have a pulley to change the direction of the string. And in here, I have implicitly assumed that the AX was greater than 0. I assumed capital M is going to be pulled toward the x direction, so I assume that. So if I want to reuse the symbol AX for the motion of the lowercase m, then I should point my axis downward. The reason of this is, well, x-axis, not y, x-axis, because this way I can write F net x equals lowercase m ax, and I can also assume this symbol ax has the same sign is positive, right? This falling mass accelerates downward, accelerating toward the x direction, so the ax is positive. So that makes things easier if I assume the correct direction for the x-axis for the lowercase m. So here we have the net force is gravity along the x. Now gravity of the little m is positive because this is just because we picked it this way. The axis is along this direction. It's entirely our choice. And then there's tension Ft in the opposite direction from the x. Okay, so we have these equations. I can call this 1, this 2 is already solved. If I know mass m, I can find tension normal force Fn. Here, this equation is not solved yet. Our goal is to find A, so let's get rid of the Ft. We can use Ft here to substitute for that. So equation 1. In equation 3, we'll have lowercase g, though, so lowercase m times g, that's the gravity of lowercase m, minus tension gets replaced by this capital M ax equals lowercase m ax, and then I can add max on both sides of the equation, then I get mg equals max plus capital max. So that is m plus m ax, or I can also write m total, mtot, ax, whichever you prefer. Okay, so now I have this, I can just divide out the mass total. I get a equals, this is x acceleration, here's lowercase m over m total, this is capital M total, times g here. So this gives us an idea how the acceleration depends on the masses. So if we have the same total mass, if we increase this little m, maybe take some mass from here and put it here without changing the total mass, if we do that, we increase acceleration. So basically, the heavier the hanging mass is, the more the whole system accelerates. It makes a lot of sense. And only under the condition the m lowercase m is the total mass, or maybe you're just pulling, you have a heavy weight pulling a feather, so this capital M is almost zero, then this lowercase m is equal to the m total, then you have a 1 factor, then ax is equal to g, right? Only under the condition you have a very heavy mass pulling something very insignificant, you'll have the heavy mass falling at gravitational acceleration, free falling. Otherwise, the acceleration is a fraction of the gravitational acceleration, right? So you can say that if this m is approximately equal to m total, what this means is m is much greater than capital M. This means ax is approximately equal to g. We have approximately free fall. But if we have the other case, m is much less than this m, which is our case for our lab, this is going to be over 600 grams. This is only a few dozen grams up to about 45 grams, so not even 10% of the 600 at its maximum. So we have this case. Then we can say that ax is approximately equal to m over m times g, because the total mass is pretty much just the capital M, because it's much heavier than the lowercase m. So with this analytical expression, we can solve for a lot of things. We can understand the situation more than just having a specific mass m and a capital M. Okay, so since we can solve two unknowns, we should just do that. We just solve tension out. So tension is equal to capital M times this lowercase m or m total times g. And I'll rewrite it, mm, m plus m, g. And I'll name this whole thing m reduced times g. So m reduced is equal to this m plus m. Let's put 3 bars. Equivalence. First time we introduce a concept, we have this equivalence. So this m reduced is actually less than m, also less than the capital M. It doesn't really matter how the masses are compared to each other. You could have 1 versus 1,000 or 1,000 versus 1, but this reduced mass is less than either of the two masses. That's why it's called reduced mass. It's less than either. So this seems to be the effective mass that is falling freely. So if you think about this, it's effective mass that is this tension force magnitude, effective mass or reduced mass times the gravitational acceleration. Thank you.